All right, continuing in section 12.3, we're now talking about the areas of polar regions. And in the book, they derive the formula for you quite well, but they remind you that the area of a circle is pi r squared. And then for polars, we have to remember that we are going to be doing the change in theta with respect to the whole circle, or the whole polar region. So if I rearrange this, the area of the polar region would then be the d theta over 2 pi, and then you have your pi r squared, because this little piece right here will give you the portion of the circle you're talking about. And when we reduce that, we get 1/2 r squared times the change in theta. So everything needs to be in terms of theta. Well, your r is typically in terms of theta. So what we end up getting is, if it's just one region, you're just going to integrate from a to b, or alpha to beta, of 1/2 r squared d theta. But if we have a situation where we have two functions, and the f of theta function is always greater than the g of theta function, and they're positive, then the integral turns out to be from alpha to beta. I'm going to put the 1/2 on the outside. Then we have f of theta squared minus g of theta squared, d theta. Very similar to how you integrate with two rectangular functions. So in example 3, they want us to find the area of the polar region, find the area of the four-leaf rose. And we know this is a four-leaf rose because the 2 right here indicates that there are 2 times 2 petals. So there'll be 4 petals on this. So the easiest thing to do would be to figure out the area of one petal and then times it by 4. Or if you graph this on your calculator, you will discover that the graph goes, if I do it right, around, down, then it comes, whoops, didn't go back in, goes over here, then it goes up here and back around. So I actually could just do this petal and times it by 4, or could just do this petal and times it by 8. So that's what we're looking at. Okay, so now we've got to figure out when that happens. If you start plotting dots for this, which is going to be the easiest way to figure this out, because your calculator will not find zeros in polar. It'll only find them in rectangular. You can pick it, but it's not going to do anything. So you can go by hand, you can stick in thetas and figure it out. If you stick in 0, which appears to be this starting point right there, you get cosine of theta is 1 times 2 is 2. So this spot is 2. Okay, which makes sense because the 2 in front of the cosine indicates how long the petal is. If I go to, I'm going to think it finishes this in 2 pi, maybe pi, and let me try pi over 4 because of that 2. Pi over 4 times 2 is pi over 2, and the cosine of pi over 2 is 0. So that's 0. So that puts me at the pole. So it appears that this dot right here is happening when theta is pi over 4, and that one is happening when theta is 0. And you can go to your calculator and you can keep changing the window on it, double check it, go into your window zoom and change your theta to go from 0 to pi over 4 and see if you just get that half a petal. And you do. So we are going to do 8 times the integral from 0 to pi over 4, 1/2 the function squared d theta, which is then going to give me, okay, the 2 squared is 4, times the half in front is 2, pull it to the outside, that's 16. What's left inside here is cosine squared of 2 theta, which I'm going to use a half angle identity on. And your half angle identity says the cosine Yeah, it's rearranged. The cosine squared of theta is equal to 1 plus cosine 2 theta over 2. So this is going to turn into 16, 0 to pi over 4. It's going to end up being 1 plus cosine squared, no, cosine of 4 theta, because the half angle formula says if this is theta, I'm over on the right-hand side, you double it in your new formula, so that's going to be 1 over cosine 4 theta over 2 d theta, which I could split and make it 1/2 plus 1/2 cosine 4 theta d theta. When I integrate a half, I get 1/2 x, or 1/2 theta in this case. Here I have a 1/2. The integral of cosine is the sine, but I have to have a 4 in front, because we're saying u is 4 theta, so du is 4 d theta, so it needs a 4 in and a 1/4 out. So I'm going to end up with a 1/4 out here. Whole nonsense from 0 to pi over 4. I'm going to leave the, I'm going to put the 16 through because it's going to make it no fractions. And now I'm just plug and chugging. So this is going to be 8 times pi over 4 would be 2 pi plus 2 the sine of pi minus 0 plus 2 the sine of 0. This is 2 pi. This is 0. That's 0. So the answer is 2 pi. The area of all 4 petals would be 2 pi units squared, whatever the units happen to be.